Hello and welcome to the second to last lesson in our series on CAD and design videos. This video will be everything about gears and and we'll eventually go into how to make a gearbox. So start off, there's a couple important things to know about gears. As speed goes up, torque goes down. So the torque is we'll go with turning power of an object. So something with like a bigger wheel will have more torque than a smaller wheel. And in gears, speed and torque are inversely proportional, which means you're always going to be trying to strike a balance between speed and torque in your gearboxes. And the main formula to know is that the amount of teeth in the output gear over the teeth in the input gear is the gear ratio. The speed of the input gear is equal to that ratio, so speed in over speed out will be equal to the gear ratio, and the torque out over torque in will be equal to the gear ratio as well. Another important thing to know is that wherever gears mesh, they will be turning in opposite directions, and we'll go a bit more into that in the next slide. So in this side, if you see this gear, it says it's going to be turning this way, and this is a 10-tooth gear and this is a 30-tooth gear. If we go back to our last slide, we know that the torque out over torque in, teeth out in the output gear over teeth in the input gear is the formula to find our gear ratio. We know that this is the output gear, this is the input, this is 3 times as large, therefore the gear ratio is 3:1. That also tells us that this gear will be spinning with 3 times the torque as this one and 1/3 the speed. So on this gear train, I want you to stop and think down a little bit about this. So once you do that, we'll move on. I'll just give you like 5 seconds to pause and think about it. So on this gear train, the idler gear, which is what we call this gear in the middle, is not actually going to affect the gear ratio in the end. So because of that, what we know is that this gear is 15 teeth and it's the output, and this one is 30 teeth and it's the input, therefore the gear ratio is 1/2, which means that this is going to be spinning twice as fast as this one, but with half the torque. So we know that because it's spinning 20 revs per minute, or 90 revs per minute, sorry, that this would be going 180 revs per minute. What the idler does do is that it makes it so that these two, the input and output gear, are spinning the same direction, which may not seem very useful, but in some applications is very useful. And this is a compound gear train. So the compound gear train is unique because unlike the idler gear train, there is these gears in the middle do affect the gear ratio. And this is not like a two-dimensional thing. This gear, the large gear, gear B, and gear C, the small one right here, are spinning on the same shaft at the same speed with the same torque. However, this gear C is meshed with gear D and gear A is meshed with gear B. So if we say that this is the input gear, actually I'll slow down. I recommend trying to figure out the two gear ratios and then multiplying them together to find the final gear ratio in this. So the first gear ratio is, the first section I'm calling A and B, is 2:1 because 32 over 16 is 2, which means that a gear here, this gear will be spinning with twice the torque as this gear. Now for gear C to gear D, that's a 3:1. And that means that this gear will be spinning with twice the torque as this one. So if this gear has what the final gear ratio this will be showing is the ratio of gear D to gear A. So with what we know that the ratio of gear B to gear A is 2 to 1, and from gear D to gear B is 3 to 1. And we know that gear B and gear C would technically be the same thing in this, just in terms of how we view them, like the forces on them. We can multiply those together and get that the final gear ratio is 6 to 1. So by using this is a compound gear train. You can get really large reductions to get things to go really fast or really slow in a good compact use of space without needing a huge gear and a little gear. So what we're going to learn how to design is called a gearbox. Now a gearbox is what we use in robotics to hold the gears in place and achieve a desired output. So there's plenty of ways to do this. I'll just go through some of the ones that we have here. This top one in the left corner is a 2-speed belt-driven gearbox. The 2 belts are in a serpentine path here going around, and there's a little bearing to tension it. And the shifters are driven off of these small little cylinders, and they shift between 2 different gear ratios further on in the gearbox to achieve different speeds and torques. This is much more complex than what we're going to be going over now, but it is important to know what they do and how they work, and eventually we can get to those. So the second one is for a lift gearbox. It uses 4 gears on a 2-stage reduction. And I should mention the stages are basically like how many different points the gears mesh at. So you can see here you have a gear meshing, the gears on the motors are called pinions. So you have a pinion meshing with a big gear here, and then in front of it you have a gear meshing with another gear below. So that's 2 stages of reduction. This is for a lift. The first one is for a drivetrain, and it was designed to be, I'll just go with it, it has a different purpose than the other one, so it's a little different from what we're going to be doing as well. Now on this side, on the right, there's a set of 3 gearboxes. These are all different styles. We aren't going to be doing one that's quite like any of these. The closest one we'll be doing is the top one, but that's still a bit complex. The top one is, I believe, a 3-stage reduction with making use of idlers and such, and very heavy, very complicated, and honestly kind of over-engineered. The second gearbox on the row, this one, is another drivetrain gearbox. We've used it 1 season, and the unique thing about this is this output shaft is on the same side as the motors, whereas on this one it's on the opposite sides. So it's a little bit harder than what we're going to do, but it's not too hard, and once we get through with this, it shouldn't be too much of a challenge to design one like that. The third one makes use of a tube, which is what the gearbox is mounted to, and uses it to hold it together. So it's just lighter, more efficient than this one, which uses a separate plate. Yeah, so now that that's all gone through, we're going to work on calculating the speeds for a gearbox for a robot drivetrain. So what I've opened up here is called, it's a file, it's an Excel spreadsheet in the file in the link in the description called JVN Design Calc. And what it does is it gives you a bunch of options here at the bottom to design a bunch of mechanisms. So you can choose whatever numbers are appropriate, and will help you simplify the process instead of having to do everything by hand. So we're just going to go through some. We have like 2 speeds, which is shifting drivetrain, so you can go fast and slow, like a high and low speed. it's another version, sorry, there's a lot of them. Single stage gearboxes, single speed gearboxes, sorry. Articulating drives, tilt mechanisms, linear mechanisms, so that's like a lift, intake mechanisms, and these are data sheets. So I'm going to go to a custom 1-speed drive, and what we're going to do is we're going to go to here. This is the motor type. So right now it's on a sim motor. We're going to switch that to Falcon 500, which is the new cool motor. All the other default settings are fine as is, and the numbers that are important are these ones. On a Falcon, just because of the way the motor works and how resistant it is to heat, this number isn't too important as long as this number is reasonable and you're using 2 motors. So the way this works is you adjust, these are your gear ratios basically. So a 1-to-1 is the same as a 3-to-3, right? And so the driven gear is a 3 and this will be a 1. That is the same as a 27-to-9. So using this, we're going to try and get a reasonable number. And the number we're going to try and get to is somewhere between like 11 and 14. So I'd encourage you to play around with this by yourself, but we are going to use like a specific combination that, how to describe it, using a select amount of gears that will be used to do the CAD for this. So the first number is a 12-tooth pinion. This will be going on the motor, so it's a driving gear, and it's 12 teeth. So obviously that made the drivetrain adjusted speed really fast. Also, this is the free speed, so like that's ignoring the weight of the robot, but the adjusted speed accounts for that. So this is the real number. The driven gear, the options for the gear teeth that we're going to be using are 12, which we've already used, 18, and 38. So we've already used the 12, and the 12 can't be used on anything else. So these are our options. So I guess we'll start off with trying to make the biggest reduction. Actually, let's just start off with making that 18, that 18, and that 38. Just trial and error, nothing too fancy. So we see that this is still too fast. So if we want to increase the reduction, we could add another stage. Now we're getting in the range we want, and this is good. So we want to be here, but this is 3 stages. That's a very, very heavy gearbox, a lot of work, and could be made much easier. So what we're going to do is we're going to get rid of this last stage and just mess around with some things until we can get it to be what we want. So we want that to be 18, that to be still too fast, so try 38 here, and that gets us into the ideal speed. So this is the setup we're going to be using. I encourage you to play around and use this as much as you want, but this will be the setup we're going to be running in our next tutorial video. Separated this into 2 parts because the next part's going to be quite long and you'd probably want a break in between. So I'd recommend watching that next, but taking some time in between just to relax because the next video is going to be quite long. So yes, thank you for watching. Look out for the next video and have a good day.